guys, welcome back to Vital Signs. Today we're talking about chemistry, my favorite. If you're new here, I'm Professor Thomas. I'm here to give you a crash course on all things anatomy and physiology. With chemistry, we start with the atom. Atoms are made of 3 subatomic particles: protons, neutrons, and electrons. Protons are positively charged. Neutrons are neutrally charged. We'll find both of those in the nucleus of an atom, the core of the atom. But surrounding those protons and neutrons, we have electrons. Electrons are negatively charged, and they surround that nucleus in orbitals, almost like planets going around the sun. In our innermost orbital, we'll have at most 2 electrons, but every orbital past that is going to have 8. The goal is to have 8 electrons in our outermost orbital. We would call those 8 our octet. Elements are pure substances. They're made of only one kind of atom. For example, carbon, calcium, iron, helium. When we take atoms and put them together and bond them, that would become a molecule. If we have different atoms coming together and bonding, that would be a compound. A great example of that would be water, H2O. We've got different guys, hydrogen and oxygen, but they're all bound together in a nice way. That's what makes a compound. Atoms will react with each other to form bonds with the goal of being more stable. They all want to have that octet. And there are 3 different bonds we're going to talk about today: ionic bonds, covalent bonds, and hydrogen bonds. With ionic bonds, this is kind of a steal and get stolen from situation, where one is taking an electron, the other one had an electron it wanted to give away. So they're both leaving the situation happy. Usually this happens when I have a positively charged ion like sodium attracting a negatively charged ion like chloride. They come together and make sodium chloride, table salt. Sodium chloride is a great example of an electrolyte. An electrolyte is something that dissolves in water. So if I'm salting my water as I'm about to boil pasta, you'll notice the salt kind of disappears into the water. That is an electrolyte. Covalent bonds are more of a sharing situation, where they are sharing that electron between them to both achieve the octet. But sharing isn't always fair. Sometimes one has a really strong pull on the electron and the other one's barely holding on. That would be a polar covalent bond. Other times they're sharing it perfectly fair. That would be a non-polar covalent bond. Hydrogen bonds are the weakest guys we're going to talk about. They involve hydrogen bound to something. Maybe it's oxygen, maybe it's nitrogen. These bonds associate and disassociate fairly fast. Great example would be a water molecule here and a water molecule there. The hydrogen on this one is hydrogen bonding to the oxygen on this one. It's a very weak bond. It'll fall apart quite easily. Now let's talk about something scary: organic chemistry. We don't need to know too much about organic chemistry. All you need to know is that it is looking at carbon-carbon bonds and carbon-hydrogen bonds. When we talk about inorganic chemistry, that is not involving carbon. The exceptions would be carbon dioxide and carbon monoxide, but for the most part, inorganic chemistry, no carbon necessary. Organic chemistry, all about carbon. Water is essential to life. Water makes a great solvent. A solvent is something that a solute would dissolve within. When it comes to water, there's 2 types of chemical reactions we want to be familiar with: dehydration synthesis and hydrolysis. But before we get into that, let's just talk about a chemical reaction in general. A chemical reaction involves reactants on the left side of a reaction arrow. The reaction arrow just means the reaction has happened, and on the right side, we're going to have products. So a dehydration synthesis involves reactants, reaction happens, and water is being released. Water is a product. A good example of this would be making brownies. You put your brownies into the oven, you open the oven, and if you wear glasses, what happens? They fog up, okay? Steam is escaping, water is escaping. That's a dehydration synthesis, where water is being released and we come out with our product, delicious brownies. A hydrolysis is the opposite. A hydrolysis reaction involves taking a larger compound, we're adding water in as a reactant, reaction happens, and we have 2 smaller products. Moving on to pH. pH stands for power of hydrogen. When we talked about water, we know the chemical formula for water is H2O. If we split that apart, we would have hydrogen and hydroxide ions, OH-. So looking at our pH scale, pH goes from 0 to 14. Anything below 7 is on the acidic side of the scale, meaning we have a lot of hydrogen ions, not so many hydroxide ions. Above 7 would be the basic side of the scale, or the alkaline side of the scale. Not too many hydrogen ions, but a lot of hydroxide ions. The pH of 7 would be considered neutral. One pH that you have to memorize is the pH of blood. The pH of blood is 7.35 to 7.45. How they can ask test questions about this is they'll give you a patient scenario. Your patient's blood pH is 7.5. What would we call this condition? Well, 7.5 is higher than normal, so we would call that alkalosis. It's closer to the alkaline side of the pH scale. But if your patient's blood pH was 7.2, that would be closer to the acid side of the scale, so we would call that acidosis. Even though 7.2 is technically alkaline, because it's going towards acidosis compared to what's normal for blood's pH, we would call it acidosis. Often in chemical labs or in a microbiology lab, we'll do experiments that require a set pH to not change too much. In experiments like that, we'll use buffers. Buffers prevent a sharp change in pH. Let's wrap up by talking about our 4 main characters of organic chemistry: carbohydrates, lipids, proteins, and nucleic acids. Carbohydrates involve carbon, hydrogen, and oxygen, and they kind of form these rings. So if we have one single ring, that would be a monosaccharide. A great example would be glucose. But when I have 2 rings bound together, that would be a disaccharide. Di means 2. Great examples would be lactose or sucrose. When I have more than 2 rings, we don't have to memorize any more names. At that point, it's just a polysaccharide. Great examples would include glycogen or amylose starch. The purpose of these carbohydrates is to store energy for later use. Lipids is where things start to get complicated. These are fat-soluble and highly diverse. We've got triglycerides, phospholipids, and steroids. Triglycerides involve a glycerol head and 3 fatty acid tails. Triglyceride, tri means 3. With those fatty acid tails, please be aware that saturated fatty acids are solid at room temperature. Unsaturated fatty acids are liquid at room temperature. Saturated versus unsaturated just has to do with whether or not there are double bonds in that chain and how many hydrogens are present. Phospholipids are similar to triglycerides, but they do have a phosphorus, and they only have 2 fatty acid tails rather than 3. Phospholipids make up our cell membranes. All we need to know about them right now is that head with the phosphorus is hydrophilic. It loves water. The tail with the 2 fatty acids, those are hydrophobic. They hate water. Steroids are molecules made of multiple rings in their structure. A great example would be cholesterol. Proteins are made of amino acids, which are held together by peptide bonds. They'll fold in very specific ways to achieve their functions. Structural proteins like collagen and keratin. We have functional proteins like hormones, and we have enzymes that help chemical reactions to occur. Enzymes kind of work like a lock and key, and they speed up a chemical reaction. Wrapping things up with nucleic acids. Nucleic acids would be DNA, RNA, ATP. They include a phosphate unit, a sugar, and a nitrogen base. The sugar for DNA would be deoxyribose. The sugar for RNA would be ribose. That's what the D and the R stand for. The nitrogen bases differ depending on whether we're talking about DNA or RNA. In DNA, we have adenine, thymine, guanine, and cytosine. Usually we just abbreviate those by the first letter. A, T, C, G. A always pairs with T. You can remember that because of the phone company. C always pairs with G. The letters are shaped kind of similar. In RNA, we don't have thymine, we have uracil. So in RNA, A goes with U, C still goes with G. ATP is a modified nucleotide. That is how our cells transfer energy to different places. And there you have it. That is our introduction to chemistry. Thanks for joining me. I'll see you next time.